Okay, so in this video we're going to calculate a Taylor polynomial for 5 terms at the point 0 for the function ln of x plus 1, and that's our function there. And important to remember that we're calculating it at point 0, that's our part of the question there. So point A is 0, and calculating it also for 5 terms. So always remember to get your 5 terms. So the Taylor series is of a degree n. So degree 5, so n is 5. So here below here we've got this generic formula for Taylor polynomial, and you'll see it's got a series of derivatives and factorials and x minus a to the power of n. Now we've already calculated that the point A is 0 and the degree of n is 5. So straight away we can substitute these a's for 0 and these n's for 5. So here 5 as well if you wanted to. So what does all this mean? So t5 of x would mean 5 degree Taylor polynomial. So t5 of x, that's the generic term for that. F of a, so that would be the function at 0. And then we've got the first derivative of calculated at a, which is at 0, divided by 1 factorial, x minus a, which would be x minus 0 to the power of 1. Then after this we add second derivative at point 0 divided by 2 factorial, then x minus a, which is 0, squared. And then there's a pattern forming all the way along here. Got the third derivative, 3 factorial, x minus a cubed, fourth derivative a, 4 factorial, x minus a to the 4, and then 5, 5 and 5. And it goes all the way along, and this term at the end is basically what would be the term for every single one if you went all the way along to even 10 terms or 12 terms, whatever many terms you wanted to go to. So next what we're going to do is we're going to differentiate the function ln of x plus 1 5 times. So here's how we're going to differentiate this function. And then each time we differentiate it, we're going to calculate the value of each derivative at 0. So we draw up a nice little table. So we first of all start off with the function, which is ln of x plus 1, and the function at 0 is 0. So the log of x plus 1, well x will be 0, so log of 1, natural log of 1 is 0. So that's pretty straightforward. And then we differentiate the function 5 times. So when you differentiate a natural log of anything, basically you take the reciprocal of what's inside here and then multiply it by the derivative of what's inside. So when we take the derivative of ln of x plus 1, we've got 1 divided by x plus 1 and then multiply by the 1 as the chain rule says, because the derivative of x is 1. It just leaves it as 1 over x plus 1. And then we could also write this as x plus 1 to the power of minus 1. That could also be easier to differentiate as we're going along. Now, as we're going to be differentiating x plus 1 in the brackets all the way along, we don't need to worry about multiplying by 1 each time as the chain rule would ask us to do, because it will make no difference to the function anyway. So now what we have to do is take the second derivative of ln of x plus 1. So to do that, we just take the derivative of 1 over x plus 1. And to get that, we get the minus 1 here, bring it to the front, and then decrease this power by 1. So as you see here, see what's happened here. To get from here to here, the minus 1 has come to the front, and then this is decreased by 1. So then we've got minus 1 times x plus 1 to the power of minus 2. Which could be written the same way, means the same as this, which is minus 1 over x plus 1 squared. And then to calculate that at 0, we've got minus 1 over 1 squared, which is just minus 1. So the second derivative at 0 is minus 1. Then again, to find the third derivative, we just differentiate this value here, this function here. So again, to differentiate this one, we bring this minus 2 to the front and multiply it, and then decrease the power by 1 again, as the power rule will always say. So minus 2 times minus 1 is 2. That's hence why the 2's there. and then decrease this by 1 again to get to the -3. And again, you can write this in this way. Another way you could have done that would be to get this -1 and imagine this 2 is a -2, and -1 times -2, then bring the 2 onto the top and then increase the power by 1. So that way then you go straight to there. So when we differentiate this function this time using this shortcut method to say keep writing these all out, you can do 2 times -3, which is -6, then increase the power by 1. That would be -6 x plus 1 to the 4, which you know is -6 x plus 1 to the power of -4 when written on a straight line rather than as a quotient. And then the value of that at 0 again is -6. -6 over 1 to the power of 4 is still -6. And again, to differentiate this function here, -6 times -4 is 24. Increase the power to get to 5. 24 over x plus 1 to the 5. And then we've written it down here as 24 x plus 1 to the -5, which is the equivalent. And again, the value of this at 0 is 24. So now we can start to expand on our Taylor polynomial to start inputting some values. So we put the n in here for 5, so t5 of x, and all the a's we put as 0. So there we go. And we can see here that is f5 0. We've already calculated all these derivatives. f4 0, -6. Third derivative at 0 is 2. Second derivative at 0 -1. First derivative at 0 is 1, and the function itself is 0. So basically we know the values for all of these values here. And this x minus a, because a is 0, we just write x in there. So that keeps it nice and neat and tidy. So now we can simplify this up a little bit more and put all these values in place of these symbols for the fourth derivatives, third derivatives, and so on. So now what we end up with is the Taylor polynomial. We could also call it a Maclaurin series if you wished, of degree 5 at point 0 for natural log of x plus 1 is 0. So f of 0 was 0, that value was 0. The first derivative we calculated was 1, which we had here. So that's the 1 there. So you put the 1 in there. 1 over 1 is where that comes from. The second derivative was -1. So we've got -1 over 2 factorial times x squared. Third derivative was 2. So that's a 2. So then we've got 2 over 3 factorial times x cubed. Fourth derivative was -6. So there we put a -6. Then we end with -6 over 4 factorial times x to the 4. And the fifth derivative was 24 plus 24 over 5 factorial x to the 5. So the next stage we can do is we can calculate all these factorial values and then maybe simplify it up with what we've got in the numerator. So for example, 3 factorial we know is 6. 2 divided by 6 is 3, so that's a third. 4 factorial is 24, so -6 over 24. So that then becomes minus a quarter. So this plus sign we can then switch it and change it to a minus. And 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. 24 divided by 120 gives you 1/5. So then we can simplify this up even more, and we end up with our 5-degree Taylor polynomial at the point 0 for natural log of x plus 1 is x minus x squared over 2 plus x cubed over 3 minus x to the power of 4 over 4 plus x to the 5 over 5. And you can see there's a nice little pattern in this series here. So you start with x, then it's a minus, then you've got the 2, x squared over 2, then it's a plus, x cubed over 3, then it's a minus, x to the 4 over 4, and then it's a plus, x to the 5 over 5. Then if you went on and on, you'd have a minus, x to the 6 over 6, and then a plus, x to the 7 over 7. So all the odd numbers will be plus x to the whatever value you're on, divided by that value, and then all the even numbers will be minus x to the power of that number divided by that value. So then you could keep going on and you wouldn't have to even work out anymore. So we just put this into a graph now and see how accurate we are. So here we go. So the dotted line is the graph of natural log of x plus 1, and that's that function there. And this solid black line is our Taylor polynomial, which we calculated And as you can see, it was asked to calculate it as 0, and at x equals 0, our function is very accurate. So we can be very happy with that correct. And it also stays correct up until it goes just past or just approaches 1, then it starts to peel away a little bit, and then our Taylor polynomial diverges off to infinity for x is larger than 0, and then diverges down to negative infinity as x is less than 0, as does ln of x+1 as well. So we can be pretty happy with that, so that's pretty good. So therefore we can conclude that our Taylor polynomial is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5. Okay, and that concludes it. Thanks for watching.